Hello, here's another batch of waves questions. So we're starting here by looking at a couple of definitions, as we often do, explain what's meant by progressive wave, and then state two differences between a progressive wave and a stationary wave. Right, we've had this sort of thing before, so I won't bother writing these out, I'll just say them. So progressive wave is a transfer of energy, but not matter, as a result of oscillations of the medium through which the energy is traveling. So you probably don't need quite as much explanation as that on this, but it's quite nice to get all those keywords in, isn't it? You know, transfer of energy but not matter. So having both of those things in, and then saying that it has to be a result of oscillations of the medium through which the energy is traveling. Right, differences between progressive and stationary waves. So there's quite a lot of them. Well, one of them I suppose I already touched on in that first definition there. So progressive wave transfers energy, whereas stationary waves trap energy in pockets. We could say, well, all points on a progressive wave will oscillate, whereas on stationary waves you'll get points, i.e. nodes, where there is no oscillation. So that would be two good differences that you could have there. You could say things about phase differences. You know, that you've got on a stationary wave, you've got everything between two nodes oscillating in phase, whereas over one cycle, one wavelength of a progressive wave, everything will be at a different phase. So you could say something like that. So there you go, that's three differences, but just pick two of those. I quite like the one with the some points oscillate and some don't on the stationary wave. Right, so part B, figure 4.1 shows at time t equals 0 the shape of a section of stretch cord along which a transverse wave is travelling from left to right. Right, so we've got that direction of travel. W, X, Y, Z, 4 points marked on the cord, mechanical oscillator causing the wave to oscillate at a steady frequency of 5 hertz. Right, that's new. Wavelength is on the picture, amplitude's on the picture. On the axis, sketch a graph of displacement of X over the period 0 to 0.4 seconds. Add suitable scales to the axes. Okay, so we're going 0 to 0.4, so that's going to be 2 cycles, because we've got 5 hertz, it's 0.2 seconds per cycle. So that's going to be 2 oscillations we're going to want here. We're doing this for point X. Point X is starting at amplitude, which is our 0.03. So let's make, say, I don't know, I'll just pick some line there. So that's on that line, let's call that the 0.03. And let's have, well, whatever the same distance is below, it's hard to see on that screen. That looks about the same, minus 0.03. And we'll say that I can't really see these lines, 2, 3, 4. Is that 4 of them? That's 2 of them. They look slightly darker lines. And we're going, so we'll make that a, well, I'll draw the shape in first. So that needs to be a peak again. That needs to be a peak again. That's going to be troughs, so we're going to have something like that for 2 cycles. There you go, that's not too bad. And then that was what, 0.2 seconds, 0.4 seconds. There we go, so that was fairly straightforward, just drawing a cos graph for that one because we're starting at amplitude. State which of the points W, X, Y and Z at t equals 0 is instantaneously at rest. Right, so we want something which is at amplitude, so that's going to be X is at rest, has the greatest speed. We want something at the equilibrium point because that's where it goes fastest, so that'd be W. 90 degrees out of phase with each other, so we need to be a quarter of an oscillation out. Well, W and X a quarter of an oscillation out, because of course an oscillation, you know, is up, back, down, back. So going from W to X, that's a 1 out difference. So W and X. So Y and Z don't even come into it, which is probably where they're trying to confuse people. On figure 4.1, oh yeah, that's that picture. Draw arrows to show the directions in which the points Y and Z are moving. Right, so the wave profile is moving left to right. So a little bit later, the wave, if we were going to draw it in, I'll change it to blue, the wave would have moved off to the side like this, because the wave's moving, the wave shape is moving right to left. So Y and Z are both going up and down, of course. So Y has now moved up to there, Z has moved down to there. So yeah, make those arrows maybe a little bit bigger. So let's do a big down arrow for Z, big Y up arrow for Y. Of course, you wouldn't have drawn in the new wave profile, so it wouldn't have gone over the top of those. But it's quite easy to think that these points W, X, Y, and Z, they're the ones that are zooming along this shape of the wave, and then people draw the arrow in the wrong direction. But yeah, it's the wave profile that is moving from left to right. W, X, Y, and Z are just moving up and down. They're not moving in the horizontal direction, only the vertical direction. That's good starter. Oh, we got more of it. Right, still on the same question. Right, the speed v of the wave on the stretch cord is given by this formula. V is a function of tension. T is the tension in the cord, K is a constant. Calculate the wavelength of the wave after the tension in the cord has been quadrupled, but the frequency is unchanged. Right, so, well, velocity is equal to the frequency times the wavelength. Here we've got that the velocity would have gone up by 2, multiplied by 2, because we can square root that 4 times tension. So the velocity has doubled. The frequency has stayed the same, so the wavelength must have doubled as well. So what was the original wavelength? I can't remember now. They told us this before, didn't they? It's 0.6 meters, so we've doubled that up to 1.2 meters. Right, last part. Speed of point W on the cord at t equals 0. So that was the one that was at the equilibrium point. So it's going at the fastest, is going at 0.94 meters per second. Cord is original tension, so we've not changed. We've not changed the tension at all. Frequency of oscillation is now doubled to 10 hertz. Amplitude is kept the same. Right, calculate the new speed of the point. Right, okay, so we're not changing the amplitude. So the distance moved in one oscillation, distance moved by particle on wave in one oscillation is unchanged. But we've got that the time of oscillation has halved. So therefore, the velocity of velocity, we could say velocity because it's going to be the velocity over the whole oscillation, but you could say speed or velocity, it doesn't really matter on this one. Velocity of oscillating particle must double. Particle is doubled because it's moving through the same distance in half the time, so it must be going twice as fast. So calculate new speed, so we can say therefore there will be 0.94 multiplied by 2, which is, what's that, 1.88 meters per second. Right, so yeah, again, something which can be confusing in waves. We've got the difference between this V here, that's the velocity of the wave profile moving through space. That's our left to right motion of the wave, you know, when we drew that thing out, and that is moving off to the right at this velocity here. So it said here that the original tension, so the tension hasn't changed, so that V there is unchanged. What has changed is you've got a different velocity, of course, of how quickly these things are moving up and down. So the higher the frequency, the faster these things are moving up and down here. So if this here has not changed, this V, where we doubled the frequency, then we must have reduced the wavelength in order to have the same wave velocity. So yeah, you can see that we've got two different velocities that we're talking about here. And this 0.94 meters per second is not this v here. It's a different velocity. So don't get those things mixed up when you're talking about waves. You know, we've got the SHM motion of the particles on the wave, and then we've got the motion, as in this case given by that formula, of the wave profile itself. So yeah, it's a nice question to get started. It sort of digs into some of the weeds on what's actually going on with waves. All right, so this must be the next question. And yes, we've got superposition of electromagnetic waves. So we're starting here in part A. Oh, we've got state, state, and state. So we're starting with more definitions. I'll just say these rather than writing them out. State the principle of superposition of waves. So when two or more waves coincide at a point, the resultant displacement is equal to the sum of the displacements of each individual wave. So you want to say that you've got two or more waves coinciding at a point, then there's a resultant displacement, which is the sum of the individual displacements. So they're the key bits that you need to fit into that definition. Right, state one property of electromagnetic waves that distinguishes them from all other waves. So we can say, well, they're oscillations of electric and magnetic fields. So that's definitely going to cover that thing that's distinguishing them from all other waves, because electric and magnetic fields only apply to electromagnetic waves. Third one, state why electromagnetic waves can be polarized, but sound waves cannot be polarized. Right, so we've got only transverse waves can be polarized, electromagnetic waves are transverse, sound waves are longitudinal. Right, so that's a nice set of definitions to get us going. Right, part B. In figure 5.1, T1, T2 are two adjacent transmitters a meter apart with a receiving aerial R halfway between. Right, transmitters are set up to emit coherent EM waves, wavelength 3 centimeters. Right, so student finds that the signal at receiver R falls from a maximum to 0 when R is moved 0.75 centimeters towards a transmitter. Explain this observation. Right, so we've got a stationary wave set up here. So we want to say that the waves from T1 and T2, so put in superpose. So we want that. I'm going to write this in sort of shorthand, but we want to get that keyword in. That's going to produce a stationary wave or a standing wave, whatever you want to call it. Either one's fine. So that's another key term that we want to get in. We're going to have constructive interference at the midpoint. So constructive interference at midpoint R. So that means we're going to have a maximum signal. Then we can say that we're going to get destructive interference, another key term, and that is going to be a quarter of a wavelength away from R, because that's our distance from node to antinode from R. So that is the node to antinode distance. And then they've given us the wavelength, haven't they? Yeah, wavelength is 3 centimeters, so a quarter of 3. So 3 divided by 4 equals 0.75 centimeters. So just put a little calculation in at the end. And the other thing that we can say about this is that the put it as a sort of bracketed note, maybe the waves are vertically polarized. They must be. I mean, it looks like we've got vertically polarized waves, because otherwise they wouldn't go down to 0 unless we've got everything, oscillating in the same, polarized way. Waves are vertically polarized. If they were just coming out with any old direction of oscillation, then they're not always going to be completely cancelling out. Yeah, I mean, you're still going to get things cancelling out, but it wouldn't necessarily go all the way down to 0. Right, so that's that first part. With R at the midpoint between T1 and T2, student rotates T2 through 90 degrees. Okay, right, so just flip that one round. Finds that the amplitude of the signal R falls to about a half. Detected signal now remains the same when R is moved 0.75 centimeters. Right, explain these. Right, well, I've used up all my space already for writing this out. But yeah, what we're going to be saying here is we're going to be, so by rotating, that's going to remove the standing wave, because now you're going to have one vertically polarized, one horizontally polarized. So we've now got no stationary wave anymore. That means that the receiver, which is going to be detecting, the receiver is detecting the vertically polarized signal, because that's what it was doing up here. That's how it was detecting all of these things. So that is going to only pick up the signal from T1. So only T1, which means we're going to again get a half a maximum at R, because we've removed all of the T2 signal. It's not getting picked up by the receiver at all. So that's why we're getting a half there. Then when we move R, there's going to be no change, or no significant change in received signal from T1, when we move the receiver just 3/4 of a centimeter, when R moved 3/4 of a centimeter. So yeah, we're just doing that switch up. They've kind of glossed over, I know it's always the case with these microwave questions, that we've got these polarized waves, but they haven't mentioned that, I don't think, in any of this for part B. They've just said you've got these transmitters and you've got a receiver, not saying that they're actually polarized. At least I can't see any of this mentioned in there. So that can throw people a little bit with this as to, well, what is actually going on? But that is what's going on, that we've got these polarized signals. So yeah, so that's quite an involved quiz. It's got another part as well. Don't think it does it? No, it doesn't. That's going on to the next question. So yeah, there's quite a lot of descriptive work going into that one. We haven't really got any calculations to speak of, apart from just this one bit of saying it's a quarter of a wavelength between a node and an antinode. So yeah, quite a lot happening in that question. Right, so here's the final one of this batch. We've got Young's double slit. So there's a diagram with the fringe pattern. They've given us the separation of the slits, so that's already in the picture. Beam of monochromatic visible light shone through these slits. Interference fringes observed on the screen. They've given us the distance to the screen. Fringe at point B is bright. Yep, okay, so they've marked the dark ones on with these splodges. And they've given us a distance for a spread of these fringes. Right, so 3 bits to this. Explain why this arrangement with 2 slits is used to produce visible fringes on the screen rather than 2 separate identical light sources. Right, okay, this is yeah, this throws up some issues. Right, I'm going to come back to this at the end. So for now, we just stick with what they expect in an A-level answer, because there's definitely an issue with the way they've worded this question. So, and I'll come back to that at the end, and we'll sort of partly go down the rabbit hole on this. But for the moment, the reason that we've got these 2 slits, rather than having 2 separate identical light sources, is that we want the light from each source, from each slit, must be coherent. So that's what you put down in order to get your mark on this one. And it's not like it's not true, at least in the the context of the classical waves and optics that we're doing. I mean, that's fine. There's just a few things that's going to be worth unpicking about that. But I'll do B and C first, then come back to it. State the phase difference between the light waves from the two slits that meet on the screen at D and B. Right, so D is a dark patch, so that is going to have to be a phase difference of pi, or you could say 180 degrees. And then B is a light patch, is a maximum, so that is going to be 2 pi. Because, well, that would be 0 there, that would be 2 pi, you know, we're going pi, and then 3 pi, we're just going up in pi's as we go through these things. So, or in blocks of 180 degrees, depending on whether you're using degrees or radians. Right, part C, use figure 7.1 to calculate the separation of adjacent bright fringes, the distance between O and B. Right, so they've given us 8 millimeters going from there to there, and that is doing 1, 2, 3, 4. So that's going to be 2 millimeters. Well, actually, let's make it 2.0, seeing as they've given us the extra 2.0 millimeters. So they've got it to 2 sig figs. So that's that bit. Show that the wavelength of the monochromatic light is about that. So that's going to be our AX over D equation. So what we got? We got 0.4 millimeters. So 4 times 10 to the minus 4 times 2 millimeters. So 2 times 10 to the minus 3 divided by 1.5 for the distance to the screen. So that is 8 times 10 to the minus 7 divided by 1.5. So that, but 8 over 1.5 is 5 1/3, isn't it? So that's going to be 5.3 times 10 to the minus 7 meters. Right, so that's all good. Right, so to wrap this up then, because that is the end of the questions otherwise, let's go back to this part A here. The thing that I don't like about this is they've put in this identical here for light sources. And, well, what does identical mean outside of maths? You know, if we're in physics, there are certain things we can say are identical. We can say that fundamental particles are identical to each other in their construction. You know, they haven't got anything going on inside them in particular. But you have to be wary about using the word identical when it comes to physics, particularly when it comes to light sources. So why do I have a problem with this description in this question? Well, if you think of the way that we've been talking about waves, this is how it gets discussed and presented in A-level textbooks, is that you've got some wave, you've got this light source, it's emitting, we draw out these wave profiles, which are these sine waves that seem to just go on forever in both directions. And we've just got one of these that we draw out that seems to be never ending. This is the image that they put into people's minds when we're talking about waves. So if we've got two identical light sources, then if we had one here and one here, well, they're both emitting these waves that go on forever. They're identical light sources, so they're going to have the same frequency. So why wouldn't they already be coherent? I mean, the way that they've described them as being identical, and the way that pre-university physics describes and presents these waves, there is no reason to have two slits from a single light source, because you could have two separate identical light sources in the way they describe it. The trouble is the way that it's described isn't actually correct, and it creates these misunderstandings. And we have got all the stuff which is, not correct, or at least not our most accurate description, in the fact that we're dealing with classical waves. We're not dealing with quantum mechanics. We're dealing with classical waves because we're just beginners dealing with waves. And classical waves is great because it still predicts and describes a lot of things that we see in the world. It allows us to create formulae like this, which is, this is classical waves. It's really useful. It describes what we see in things like Young's double slit, but it's not our best description of how waves behave. But parking even that to one side at the moment, this idea that they plant in people's minds of having this never-ending single wave profile that's coming out of a source is what's causing a problem here. So say you've got a particular source. What's actually happening is you're getting these, you're getting multiple of these waves coming out. You know, you've got a lot of stuff going on inside a light source. Yeah, there are a lot of things that are emitting waves. There are a lot of things that are starting these oscillations, and those things that are starting these oscillations can also start and stop. So you get these things that are called wave trains. So you'll get some like a wave train that will come out that'll be, you know, 3 oscillations or whatever, and then a little bit later you might get another one of a little bit coming out, and then you'll have another one. So you're getting lots of these little bits of oscillation which are arranged in certain ways. Okay, they might all have the same frequency, but they're arranged relative to each other in different ways. You know, you could have 3 that are like that. You could have 3 which are all completely stacked up. Okay, they're all emitting at exactly the same frequency, but they're arranged relatively to each other in a different manner. So if you've then got what is 2 identical, whatever the hell that means, light sources at these 2 points, we don't know if we're going to get these wave trains aligned in the same way. Okay, all of the trains have got the same frequency, but that doesn't mean to say that they're going to be coherent, because of course the coherence is we're talking about the phase difference between these trains. So that's why we need to have a single source, or at least that's why in the context of classical waves we need to have this single source. There's going to be other ways of describing this when you get into quantum mechanics. But I just feel as though they really leave this hanging when they're describing this at A level, because of this picture that they create of just a single wave profile. Yeah, so that's why. I mean, if you've got now the one source, if that's coming out with, you know, wave train 1, wave train 2, wave train 3, then we're going to have the same 3 wave trains turning up at each slit. They're still going to be completely coherent with each other. Whereas, as I say, if you've got 2 different sources, okay, it's going to be at the same frequency, but you might have one of them doing that and the other one might be doing, you know, that, in which case they're not coherent with each other. So yeah, we've got a big hole that they leave in the description that then just suddenly appears when they throw in stuff like this into an exam question, which I can only assume they've done because they haven't actually thought about what they're teaching. It's just bewildering, and it confuses people if they start thinking about, well, what does that mean? Why on earth, if it's identical, then why call them identical if they're different? Mystifying. Right, so that's my rant on that one. So I suppose the takeaway on that is, I mean, you don't need to know all of this stuff at the moment about wave trains and all of this. It doesn't come up in any of the A-level questions. You can still write that down, you know, light from each slit must be coherent in order to get your mark. But keep this in mind if you're going on to do physics at university, that there are significant issues with the classical description of waves that you are then going to have to replace, or at least supplement, when you start studying waves at university. You know, you need to get away from, well, this particular thing. You need to get away from the simplified idea of having these photons whipping through space like particles in the way that we talk about, I mean, classical physics, compared to, well, what's actually going to be going on when you move into quantum mechanics. So there's a lot of stuff in waves that needs to be redescribed when you start your undergraduate career. But yeah, I thought I really had to mention that there, because I just don't think, from what they teach people at A level, that part A here in this question makes any sense. I think it's just confusing and wrong. So there you go. Anyway, that brings this set of 3 questions to an end. It's a really nice bunch, actually, which has probably led to quite a long video. But there you go.